Swayam Prabha. Digital India. Educated India.
So, continuing with the discussion on forces in protein folding, we looked at these being the major contributors, right? Electrostatics, hydrogen bonding, van der Waals, local, hydrophobic. We went through a couple of issues before we actually started looking at electrostatics. One was the range of forces, right, and the other one was local, non-local interactions, right. These have to be defined when you talk about proteins essentially or any polymers. Then we started with electrostatics. That is what we are going to continue our discussion on. So, last class what we looked at, just a quick recap. So, we looked at this length known as the Jerome length, right, and this is equal to, as we said, or represented by L of B, right. And what did we say the significance was? The significance was, if we have a potential energy of interaction V of r, then Jerome length is defined as that length where V of r is equal to R T, if I am talking about an Avogadro number of molecules, right, or is equal to K T if I am talking about one molecule, right. And then we said, we actually showed an example or looked at an example of what this RT essentially means, right, and we discussed that if salts would how would sodium chloride ionize in water, as you would see that at that distance or whatever distance you have this inter lattice or inter ionic spacings in the crystal lattice, then it would be just equal to 2 RT, right, from last class, and hence because it is almost equal to your thermal energy, that is why they cannot remain as an ionic bond, like your crystal lattice energy that gets disrupted and they dissociate and dissolve in solutions as independent species, right. You knew this in terms of your lattice energy, right, like this Born-Haber cycle you have done in inorganic chemistry and all these things, you can do those, but now you are in the solvent form, that is in water, where you put in the dielectric constant as d. Now, electrostatics, let me tell you one more thing. So, electrostatics, why do people really care about it? Now, we will see as we go through the course. It plays a central role in biology. It plays a central role in biology, and that is why we have to care about electrostatics. Now, what do you mean by central role? What I mean is this, that means there is present every time we talk about a biological molecule. You talk about a protein has different charges, a protein has salt bridges, right. Now, depending upon the charge of the protein, say at a certain pH, a protein has say positive charge, then around the positively charged protein, what would you find mostly? Mostly negative ions coming from your salt or whatever you have in solution, right. Now, the question is, okay, given a system like this, how can we describe the charge distribution? How can we look at the charge distribution as a function of distance from the protein molecule? What does it mean? What it means is, if I do have a protein molecule, right, if I do have a protein molecule, say a globular a spherical protein molecule, the charge agglomeration or accumulation would be maximum near the protein surface. But as you slowly move away from the protein surface, what happens? That would slowly die down, right, because the effect of the protein slowly diminishes. That is something we are going to look at today, right. So, The topic we are going to start today is the Poisson-Boltzmann equation, which describes the distribution of charged particles slash mobile ions coming from your salts with respect to a specific charged particle, Now, this charged particle in our discussion actually would be a protein. That is where we are trying to go finally. Okay. So, let us look at a picture. Always a picture is always worth 1,000 words. So, let us look at a plane, right. It is a plane. I am given a plane like this. So, let me draw it. So, suppose this one is a plane, that means a planar surface, essentially a 2-dimensional surface, does not matter what it is. Now, what I am saying is, or what we are saying is, this plane is essentially negatively charged, right. Okay. Let me extend this. This coordinate, x coordinate is your distance x from the plane. So, this you understand, right. So, if you have a plane, this is my x coordinate, I am slowly moving away from the plane, right. Now, if I am moving away from the plane, how will my charge distribution vary? Now, if I have a salt solution, I would be having both what? Negative and positively charged ions. Because the plane is negatively charged, what should I be having mostly near the negative charged plane? Positive ions, right. So, what I can do is, I can draw a potential like this or a distribution like this, which goes this, and this one corresponds to n plus. What is n plus? N plus is the concentration of positively charged ions, that is number of ions positively charged per what? Unit volume, isn't it? That is how you define a concentration. Now, you can see what happens. Do not worry about how this function looks or how the distribution of n plus looks, but you can at least rationalize, right. That means, the closer you are to the negatively charged plane P, the concentration of positively charged ions, that is n plus, would be high, right, because there is attractive potential. As you slowly start moving away, what happens? The concentration of negatively charged ions would fall, decrease. Okay. Now, how quickly or how slowly it will fall will depend upon something else. What is that? It will depend upon the intervening salt ions we have, right, because these salt ions would potentially screen certain charges from each other. For example, if you have a planar particle which is negatively charged, if you have another planar particle, say, which is negatively or positively charged, does not matter what it is. If you have intervening salts, then depending upon what the concentration of my salt is, the distance through which these two planes would experience their attractive or repulsive force would be determined by the number of charges we have in between, right. And that is essentially what we are going to look at, that is how our charge distribution varies with respect to a static or fixed plane, and then take it over to a protein molecule. But before saying too many words, let us look at this again. So, this was n plus, but our solution is electrically what? Neutral. So, I should be having n minus 2, but n minus should be staying away from this, right. So, if this is the decaying potential, I can say, or decaying graph, I can say this would be looking something like this, which is here, this one is for n minus. Why? Because n minus near the plane would be the least, because the plane is negatively charged. So, it will repel the negatively charged ions, and as we move far away, what will happen? Their concentration would grow. That is essentially what you are seeing, right. Now, how to put it in a mathematical format? So, what we do is, keep this figure in mind, we will refer to this all the time. What we will do is, we look at something known as charge density. We will look at something known as charge density given by rho of x. And what do I mean by charge density? What is density? Or charge density, it would be charges per unit volume, right, essentially. But in this case, remember, when we are taking rho of x, it is like your one dimensional Schrodinger equation. It is a one dimensional problem. I am just taking it along one dimension. That is why I am saying rho of x. I am not saying rho of x y z. Okay, we are just starting with a very simple picture, like you did in quantum mechanics for a particle in a 1D box, like a one dimensional box, right. Now, if I look at rho of x, okay, I am going to look at rho of x now. Now, this probably you guys know, I can say n plus as a function of x is equal to n infinity. I will tell you what infinity is, e to the power minus z e psi of x over k t. I will tell you what this means, but just for the time being, we consider this coming from your Boltzmann equation. Now, what are we looking at? What do I mean by n infinity? So, if you go back to the slide again, or the slide means the previous figure, see, infinity means an infinite distance. That means this is for me n infinity. That means I have moved at an infinite distance from the plane. Okay. Now, come back to your Boltzmann equation. What do we have here? We have n plus x, that is a concentration of positive ions, so number of positive ions per unit volume, is equal to n infinity, that means whatever you have at infinite, times e to the power minus z e psi x by k t. What is z? You guys know, is the charge of that respective ion, right. What is e? Is the electronic charge, right. What is psi of x? Psi of x is the corresponding electrostatic potential. Psi of x is the corresponding electrostatic potential, right, and we will see what it means very soon. But just for the time being, try to understand the relevance of this equation. Try to understand the relevance of this equation. If you remember Boltzmann equation, do you remember Boltzmann's equation? What does it say? You have n, say number of molecules at a given state, energy state I is equal to what? n0 e to the power minus e over kt. Isn't this one very similar? That is essentially what you are looking at, right. And this one, if you take it just like that, psi is a potential, E is a charge, I mean electronic charge, and Z is obviously the corresponding valence or the actual charge on the ion. These also have an energy contribution. So, what you are looking at is essentially something which is very similar to energy, that is what you are looking at. So, now at least do you understand where this expression comes from, right? It is just nothing, these three together represents form of energy, okay, and that is why you write Boltzmann equation. Now, if you look at the total charge density, rho of x, I can write it as a summation of all charges present, all charges. That means I can write sigma I, where I is the ith charge, a summation of I, Z I E n I I can write like this. What is Zi? Again let me write it, it is the charge or valence on the ith ion, right, and obviously Ni you know is the number of ions. But guys, when we talk about the total number of ions, we also have negative and positively charged ions, right. We have already seen before that n plus of x is equal to n infinity to the minus z of e psi x over kt. Now this is for n plus, this was for n plus. I can write a similar equation for n minus. So if I have to write a similar equation for n minus, then what I can write is, tell me what I should write now. N minus is equal to, again I say n infinity, then e to the power, what should I write now? It should be plus, right. Why? Because now the z itself is negative and we have a negative sign out there, so it becomes positive, right. So we have z e psi of x over k of t. Okay. So then I can express my rho of x as, now look at this, I can express my rho of x as z e, okay, z e, then what I can write? I can write n plus n minus, that is the total, n plus n minus. So I will skip that step and I will write this is n infinity e to the power minus z e psi of x times k t, right. Then what should I write? Go ahead, I should write n infinity, then e to the power plus z e psi of x k t. Okay. Now remember, your n plus and n minus, they have what? Opposite charges, don't they? N plus and n minus, they have opposite charges, right. So what I can just put a negative sign out here, just to take the charge effect into consideration. Now this is your total rho of x, okay, this is your total rho of x, that means the total charge density. But how do I relate it to something more fundamental? So remember, when we started with this, we said it was a Poisson-Boltzmann equation, isn't it? We said it was a Poisson-Boltzmann equation. We have looked at the Boltzmann equation, but where does the Poisson come from, right? So the Poisson equation, I will not show the derivation, just take it from me. The Poisson equation is known by this: del square psi, where psi is the electrostatic potential or contribution, is equal to minus rho times d over say epsilon 0. So this equation is known as the Poisson equation. This equation is known as the Poisson equation, and you know what rho is already. Rho is the charge density. What is d? D is the dielectric constant. We know what epsilon 0 is from previous class, it is the permittivity in vacuum, right. So that is your right hand side of the equation. Come to the left hand side, the psi you know is the electrostatic potential, right. What is del square? Laplacian. So del square is a Laplacian operator. And del square in the general terms, is given by what? Del 2 over del x squared in Cartesian coordinates, then del 2 over del y squared plus del 2 over del z squared. That is what you know by your Laplacian. So now can you realize why it is referred to as the Poisson-Boltzmann equation? This is your Poisson equation. You have the charge density expressed in terms of what equation? The Boltzmann equation, where n plus was equal to n infinity to the minus that stuff. So, essentially what do we have here? We have combined two stuff, right. We have combined the Poisson equation with the charge density which is already there in the Poisson equation, where we have an expression of charge density coming from the Boltzmann equation. These two in combination give you the Poisson Boltzmann equation. Are you guys okay with this? Absolutely fine, right. So, now let us focus on this Poisson equation. Let us focus on this Poisson equation. Let us name it equation 1, right. Should have done it on the right side, but I have already written it there. Then I can write del square of psi is equal to, see, look at the Poisson equation and think about your Schrodinger equation, your H psi is equal to E psi, right. Here also you have an operator del square psi. So, you also need a psi out there, right, and where does your psi come from? Your psi comes from rho, because you have a psi out there, you check. So, then del square psi is equal to, now there is a minus sign, well we will take the minus into consideration. So, I can write it as 1 by d epsilon 0, right, and then what can I express this one as? This rho I can express as, I can take n infinity outside, then what am I left with? I am left with e to the power minus z e psi x over k of t, then minus e to the power z e psi x over k of t with a negative sign in front. See, now you have psi on both sides of the equation. So, you understand what you are going to do, right. That means, if you are going to solve this equation, like when you solve Schrodinger equation, what do you get? You get psi, which is the wave function, obviously along with the eigenvalue, the energy. Similarly here, if I am going to solve this equation, what am I going to get? I am going to get psi, provided I know what? Provided I know d, provided I know the number of ions and all these things. So, this is the or one of the major equations or most important equations in electrostatics, where on solution of this problem you will get the electrostatic potential that your charged particle is giving out. That means, the salt or ions around your charged plane is experiencing this potential of psi of x. Is everybody clear with that? Okay. So, I will do a small algebraic thing. So, what I will name this as equation 2, and what I will do is I will write this one as del square psi is equal to n infinity by d, right, epsilon 0, okay, and I can write e to the power z e psi x over k t minus e to the power minus z e psi x over k t. So, this is equation 3, okay, but I am missing one thing. Can you tell me what I am missing? So, I missed that. So, what I missed was, if you look at this equation, I should be putting what? I should be putting z e out here, and then automatically it will also come here, right, z e. Now, we will do a simplification. If you guys know, your sine of hyperbolic x is given by half of e to the power x minus e to the power minus x. This is an expression for sine hyperbolic in terms of your exponential function, okay. Let this be 4. See, if I have this, I express, so here you know what x is, your x is your z e psi x over k t, that is your x, okay. So, where x is equal to z e psi of x over k of t. Then my Poisson equation or Poisson Boltzmann equation becomes del square psi is equal to, I should be having a factor of 2 infinity z times e by d epsilon 0, then I can write sine hyperbolic x is equal to 2 n infinity z e by d epsilon 0 sine h, let me put in x z e psi of x over k of t. Okay. And this should be my equation 5. So, this equation guys, you are okay with the derivation up till this far, right? You have followed the steps. Now, this equation, this derivation you have to remember. Now, this equation is known as the non-linear Poisson Boltzmann equation. This is known as the non-linear Poisson Boltzmann equation. So, if it is a non-linear Poisson Boltzmann equation, the problem is you cannot solve it in a straightforward manner. The only way of solving it is to do a numerical solution, but we will simplify matters for us. What we will do is we will make an assumption. The assumption we are going to make is now that psi of x is small. That means psi of x is small, that is the electrostatic effect is small, and if that is the case, then can I write this Z e psi of x over k of t is much less than 1. So, what am I saying again? What I am saying is my electrostatic potential is much smaller with respect to the thermal energy kT, because this kT represents my thermal energy. Okay. Now, based on this assumption, what I can do, remember that sin h of x, that hyperbolic x is equal to what? Half e to the power x minus e to the power minus x, right? That is what it was. Okay. Now, what is e to the power x if x is small? 1 plus x square by factorial 2 and so on. Then what is e to the power minus x equal to? 1 minus x plus x square by factorial 2 and so on. But because x is much less than 1 or x is very small, what I can do is I truncate at the linear term. That means I remove all the higher order terms in the expression. Is that clear? So, what am I left with then? E to the power x, I will left with only this one. E to the power minus x, I will left with only what? This one. Okay. Now, go back to your original expression, what we started with. This was your non-linear Poisson Boltzmann equation. What did you have? This was sin of h, which was half e to the power x minus e to the power minus x. Now, you have made the assumption that x is very small, right. So, what will this boil down to? This guy, what will this boil down to? So, I can write that sin h of x is equal to, based on our assumptions, half, the first one is what? E to the power x, which is 1 plus x. The next one is 1 minus x, excellent. So, what do we get? We get x, and this x as we had defined was Z e psi of x over k of t, right. So, my non-linear Poisson Boltzmann equation now looks like this. So, what does it look like? It looks like del square psi is equal to, what are the factors I had? The factors I had were 2 n infinity, right, then z, then E over d epsilon 0. Now, this whole sign of hyperbolic x gets replaced by what? Only x. That means times z of E psi of x over k of t. To simplify it, I get 2 n infinity z squared E squared over d epsilon 0 k t times psi of x, right. So, this should be what, equation number 6, I get. So, what do you think is the major difference between equation 6 and equation 5? Equation 5, as we discussed just now, was a nonlinear equation and we had to solve it numerically, but now we made this assumption, right, that x is small, and if x is small, what I have done is we have transformed a nonlinear problem to what problem? A linear problem by doing this assumption, and hence what we say is that this equation or equation 6 is known as the linear Poisson Boltzmann equation, or do you know what is the other name of it? This is something very familiar to you. Yes, it is known as a Debye-Hückel equation, because it was first formulated by Debye and Hückel. You guys must have studied at some point of time the Debye-Hückel limiting law, right? It actually comes from this. So, what you just saw was your formal derivation of your Debye-Hückel limiting law. We have not yet gone there, but this is where everything starts. So, from first you took a charged plane, you took some mobile salt ions, you looked at the charge density, and then you expressed the charge density in terms of the Boltzmann equation. After that, you related the charge density to something known as the electrostatic potential through the Poisson equation. You combined Poisson and Boltzmann, that is why it is called the Poisson-Boltzmann equation. Then we saw that in its fundamental form it is a nonlinear type. We make the assumption of low psi of x, a low electrostatic potential, and then we simplify it to the linear regime or linear Poisson-Boltzmann equation, which is also known as the Debye-Hückel equation, right. This is a fundamental equation for you, which you guys have to keep in mind and realize the importance of this. So, writing down the equation again, okay, just bear with me. So, if I write down del square psi is equal to 2 n infinity z square E square over d epsilon 0 k of t, then psi of x. This I can write to be equal to kappa squared psi of x. This is, say, equation 7. So, this is kappa squared. So, I can write kappa squared, which is this guy. So, what is my kappa squared equal to? My kappa squared, based on our definition, is equal to 2 n infinity z squared E squared by d epsilon 0 k of t, right. So, let this be 8. Now, what is the relevance of kappa squared? Now, let me tell you the relevance of kappa squared. If you put in all the respective values out here, that means the units, I should say, you would see that kappa has the unit of meter inverse. This is in the SI form. This is in the SI unit, meter inverse, right. That means it is the inverse of what? Length. That means 1 by kappa would be having unit of length, right. 1 by kappa would be having the unit of length. So, what do you think is the significance of this unit of length or this 1 by kappa? This 1 by kappa is referred to as the d by length. So, 1 by kappa is referred to as the d by length. What do you think is the significance of this d by length? What do you think it should be? It is very simple actually. Remember the Jerome length where V of r was equal to r of t or k of t. That means if your length is beyond Jerome length, you are definitely going to have full dissociation. Why? Because your thermal energy totally overrides whatever intermolecular force of attractions you have in terms of your attractive potential. Now translate the same idea to this one. What does 1 by kappa mean, which is the d by length? D by length means, this d by length means at that length 1 by kappa, the particle or the ion would still feel the effect of the charge of the plane P. Remember the plane we started with. Okay. So, that means at this length, the ions would still feel the effect of the potential from the negatively charged plane that we started with, right. Our plane was negatively charged. In other words, what we can refer to it as is 1 by kappa is something known as the screening length or related to shielding of charges. What do I mean by screening or shielding? By screening or shielding, this is what I mean. That means if you have a plane P out here and if we are at that d by length 1 by kappa, it is still feeling some effect of the plane P. You move beyond that length, the effect is no longer there, right. The effect is absolutely no longer there. This is why it is one of the most important things. That means under a given, for a given system, given number of ions, that n, the concentration, the given dielectric constant, you can estimate from a given plane or a surface up till what distance are your ions going to fill some effect of this particular charged particular plane. Are you guys okay with the discussion on this, right, the inherent meaning? Now second, look what kappa depends upon. Kappa or kappa square, anyway you have to put a square root over it to get kappa. What does it depend upon? It depends upon n infinity, which is the concentration essentially, Z, which is the valence or the charge of the ion, E obviously is the electronic charge. That is what it is directly proportional to. What do we have in the denominator? We have temperature, we have the dielectric constant. So see how many different physical parameters can affect this kappa. It is not only a concentration of ions, it is a unique feature out there. It is not only your charge, but it is also your intervening dielectric constant, and it is also the temperature at which you are measuring this, because temperature finally or after all is a measure of what? Your thermal energy. So you always will have to take the temperature into consideration, because you started with Boltzmann's equation, right, where temperature is playing a significant role, right. Now guys, translate this and think about something you know from chemical or from chemistry point of view. There is a parameter I. What is I? Ionic strength. What is ionic strength equal to? Half summation of Ci Zi squared, right. Do you see that coming in here? You do, right, because n infinity is essentially what? Your concentration, that is number of ions per unit volume, right. You have the Z, which is the charge, right, and then you can actually put in your ionic strength in this equation. Okay. So, what that is our next point. So, what I can now say is then that if we want to invoke ionic strength into this equation, we use I is equal to half sigma I Ci Zi squared, right, and use this in the linear Poisson-Boltzmann equation to get a relation between kappa and ionic strength. Apart from the assumption of the fact that the electrostatic effect was really small, there was one more assumption we took before. Can you tell me what? When we did the derivation, there was one more assumption we took. Just look at the derivation. Let me see if I can go back to that page where I did the main thing. Look at this one. Look at this expression, rho of x is equal to Z e, right. Why could I take Z e out? On what premise? See, E is electronic charge, that is not a problem. Huh? Not only neutralization, well, neutralization will be there, but why can I take Z common? Charges are same, right. It is like sodium chloride. Z plus is equal to, or Z plus is equal to 1, Z minus is equal to 1 or minus 1, right. So, that means that Z, the magnitude of the charge is the same. That is why I could take Z e out. If it had not been the case, then I would have to maintain that asymmetric condition and actually do the problem. So, this was the other assumption, that means it is like a 1:1 electrolyte, sodium chloride, that is how I could do it. Okay. But this is also valid for anything where you do not have this symmetry maintained, that is why that is an asymmetric situation. So, do you have any questions with respect to the derivation of this Poisson-Boltzmann equation? So, my request to you guys is, for the exam you have to know how this derivation was done and the significance of the different parameters, especially the d by length kappa. You have to understand the significance of that, and to understand the significance of that, let me actually go to the slide and show you a quick example. So, this is an example of computing d by length, right. So, if I can get this slide going, for z equal to 1, what I am doing, I am computing the d by length for z equal to 1, d is equal to 78.5, that is a dielectric constant. Concentration I have taken C to be 0.1 moles per liter, right. So, if I do a d by length calculation based on whatever we have derived, the d by length comes to be, which is 1 by kappa, 9.62 angstroms. Okay, the d by length comes to be 9.62 angstroms. Now, this is left as an exercise for you to do. Okay, it will come as 9.62 angstroms, given the fact Z is equal to 1, D is equal to 78.5, the concentration C is equal to 0.1 moles over liter. I am giving you the concentration right away, right. So, please do it you will understand how people do these calculations, because d by length obviously has a very important place in electrostatics in chemistry. Okay. Now, look at what happens to the d by length at various salt concentrations. See whether this makes sense or not. If you have the concentration moles per liter and then you have the d by length on the right hand side, what happens to the d by length as we increase the salt concentration? It decreases. Does it make sense to you? Why should it decrease? Exactly, that means your concentration is not increasing. If your concentration is increasing, that means between this ion and this P you have more and more ions coming in, hence obviously the length is going to come closer, because you have too much of shielding, too much of screening depending upon the concentration. So, this is a direct fallout of what you just derived. Okay. Now, in the rest of the class, whatever time I have, well, I do not have much time, but I will just do a quick derivation and you will see what I mean. So, here what I am doing is I am actually trying to calculate the potential psi of x. I am actually trying to calculate the potential psi of x, right. Now, when I am trying to calculate the potential psi of x, I am sticking to a one dimensional problem. That means I am only taking the x axis or the x direction, and I am solving this equation, your Poisson equation that we just derived. Del square psi is equal to what? Kappa squared psi. That is what we just derived, right. Del square psi is equal to kappa squared psi, where kappa square has the usual thing. Now, if this is the equation you are going to start with, I am trying to solve for psi. Remember, I am trying to solve for psi. Because it is a one dimensional, my del square becomes what? Not d by dx, del square over del x squared, right. Then it becomes a differential equation you have to solve. If you solve the differential equation, by taking that del square is equal to del 2 over del x squared 1d, right, and you take a trial solution of say psi to be e to the power alpha x, you have to go back to your differential equation solutions, right. Then what are you going to get psi to be? Psi to be a e to the power minus kappa x, right, plus b e to the power plus kappa x. Why? Because when you put e to the power alpha x in this equation, what do you get? You get e to the power alpha x times alpha squared minus kappa squared is equal to 0. Do you understand? Because you are differentiating it two times. So, dx of e to the power alpha x is what? Alpha e to the power alpha x, then d2 over dx square is alpha squared e to the power alpha x. You also have a psi out here, you can bring kappa square on this side. The equation I am going to solve is therefore del 2 psi over del x squared minus kappa square psi is equal to 0. This is the one you are solving, right. So, you can see you already have a solution, that means you already know here what your wave function is, not wave function in this case, it is what? The electrostatic potential. After this you start applying boundary conditions, okay, and this is where we will start off in the next class based on this solution, but I will tell you what the boundary conditions are to just end the class. You can understand one thing, x can be infinity and the other one is x can be 0. X 0 means you are close to the plane, just right on the plane. X is equal to infinity means you are at infinite distance from the plane. At x equal to infinity, what will happen to psi of x? Remember, psi of x is from the plane, it should be 0 because you are much farther away than your d by length. So, if it is 0, that means psi would be 0. So, you can understand if you put x equal to infinity here, this guy goes to 0 anyway, because it dies out, right, but this one does not go to 0, this one cannot go to 0, but your psi has to go to 0 at x equal to infinity, then which one will go to 0? B will go to 0. Did you get it or not? Look at this, if you put in x equal to infinity here, in this we will do it next class, but just think about it. If you put in x equal to infinity here, this is e to the power minus infinity, it goes to 0 anyway. What about this? This is b e to the power infinity, but I know that psi at x equal to infinity is what? 0. This one cannot be 0, then what will be 0? B will be 0. This is how you did it for a particle in a 1D box, if you remember or not, right, applying your boundary conditions. What is the other boundary condition? The other boundary condition is, that means your b is equal to 0, so your psi essentially is a to the power minus kappa x now. Your other boundary condition is x is equal to x 0. When you have x is equal to x 0, then psi is equal to psi 0, which is the surface charge on the plane P, and then we get A in terms of psi 0. That is what we are going to look at in the next class. So, that day what we will do is, this we did for a plane, but now remember proteins are not planar molecules, right, proteins are what? Spheres. So, we will actually look at del square in terms of a spherical symmetry or spherical potential, and try to think what you solved for your del square, or when you used your hydrogen atom, what did you do? Used a spherically symmetric potential. We will go to spherical polar coordinates, okay, and only take the radial distribution or the radial part of the Laplacian operator. Okay, okay, thank you.